Hello everyone, and welcome to another episode of CCEL Office Hours, where we dive into the brilliant minds of the innovators who are driving the future of computing at CCEL. My name is Daniela Rus, and I'm the director of CCEL. Today we have a very special guest, Professor Tom Layton. Tom is distinguished MIT professor, beloved member of CCEL, and co-founder and CEO of Akamai Technologies, the world's leading content delivery network provider. Tom's research on network algorithms has laid the foundations of his company and made a huge difference in how you receive your information today. So let's dive into Tom's research journey at CCEL. Tom, it's so great to have you here. Your work and your impact is so inspirational and it's legendary for us at CCEL. And it goes back to the 1990s when you were a professor and you had some brilliant ideas that ended up having huge impact. Can you walk us through what it was like in the 1990s at CCEL when you were such a big innovator in the field of networked algorithms?
Really an exciting time at then the Lab for Computer Science. CCEL didn't exist yet. In fact, I remember actually first coming to MIT as a grad student. That goes back to the late 70s. And then, the work being done in cryptography was going to change the world. My first advisor, Len Adelman, and Adi Shamir was visiting, and Ron Rivest ran the theory group. Then, of course, you get to the 80s, Goldwasser, Macaulay. It's amazing what was happening in the Lab for Computer Science. It was really the who's who of theoretical computer scientists, people working on algorithms.
A walk among Turing Award winners.
Yeah, now you go fast forward, big prize winners, and of course it changed everything in the field. And then you go to the 90s, and my group was working on algorithms for large-scale networks, theory, writing, proving theorems, and how would you route packets and store information so that you could do it really efficiently. All mathematics. And Mike Dertuzos really was very instrumental, made it sure we had really great people with great collaboration, a fabulous environment, and recruited Tim Berners-Lee to be head of the Web Consortium, and his office was down the hall. And so his group and my group, the algorithms folks, got together and talking, and that ultimately led to a lot of the stuff that led to Akamai. But just a fabulous, innovative, cross-disciplinary environment in the Lab for Computer Science.
People often ask me, what is the secret sauce at CCEL and at MIT? So what was it like about those times? Computer science was still a very young field. The visionaries and the innovators were all at MIT, were known for the wild and crazy ideas, and were known for cooking them up in the middle of the night. What was it like?
I remember we would, before the conference deadlines, we'd be up all night, maybe 2 nights in a row, getting the papers in just in time. And yeah, a lot of wild and crazy ideas, a lot of excitement, great collaboration, engagement with students, faculty, postdocs. And you don't think about it at the time, but a lot of those wild ideas were going to change the world. And then you see it, now you fast forward to today, and it's like, oh my goodness, the things that happened here back then that just at the time were just a lot of fun, and doing cool research.
Tell us a little bit about the research you were doing at that time, especially about some of the insights and technical ideas that ultimately led to this huge impact of computation on communication networks.
It was all theoretical, and that meant we weren't constrained by any practical realities. The ideas we were thinking about, the conventional wisdom would be, well, you could never do anything like that in practice. You think about routing packets in the internet, well, you just use BGP like everyone else. But in our case, well, you could do it faster, at least mathematically, and prove a theorem if you sent the packet over here and then to there. And even though it looks like that's longer, turned out to be a lot better for congestion and make the whole thing work better. You think back then, and with websites, they were in one place, and maybe you had a mirror site. And that's just the way it was done. Of course, pretty quickly it was realized that's a problem. You know, and Tim Berners-Lee, he knew that was going to be a problem way back in the mid-90s. And that's when, you know, he approached our group saying, there's got to be a better way here because you get popular content and there'll be a lot of traffic to the website, it's going to crash. And it did. And, you know, back then, www stood for World Wide Wait in the early days. I remember even things like DNS. Back then, the protocol standard was you gave one resolution for a name. Now, it could be a few IP addresses. It was limited by the size of the packet to a small number. In our case, we weren't constrained by those realities. So we said, hey, when you do the lookup for DNS, you should refer it to a local server and not have it be everybody goes to the same place, which broke protocol. And people told us, you can't do that. Well, we were, you know, theoreticians. So yeah, we can do it because it's math. We prove our theorem and it works better. And then in practice, we implemented it. And yeah, it works a lot better.
What do you see as the role of analysis and understanding a solution that you deploy in the physical world? Today, we deploy a lot of solutions we do not understand, which is quite different from taking this more rigorous approach and saying, we're going to solve this problem, we're going to understand its scope and its limitations, and then we're going to do something with the solution.
It makes a big difference when you can prove theorems and do a rigorous treatment of how this algorithm, this system is going to perform under certain conditions. And that made a big difference for us when we actually implemented it, which is a whole different exercise to take theoretical algorithms and, you know, code it up into a system. But when you did do that, you would have confidence that it was really going to work in a variety of environments. It would really be fault tolerant. It would really be fast. And that makes a world of difference because often if you don't have that and you build a system, you find out, there's all these things that blow it up, or you try to make it twice as big and it doesn't work anymore. We didn't have that problem because the theory really worked.
When you solve a problem theoretically, you make a set of assumptions and then the solution is subject to those assumptions. Then when you take the solution, you move it into the physical world, you have to ask which of those assumptions hold. Did you find that all your assumptions were okay for the physical world, or did you have to innovate?
Oh, there's a lot of innovation. And of course, when theory meets practice, you know, that's not an easy thing.
Yeah, there's always a big step from theory to practice.
Yeah, and of course, we were all theoreticians, didn't really know how to code all that well. We were fortunate that we hired and worked with a lot of people who were very good. Way back in the day, Bonnie and I coached the MIT programming team.
Oh, that's awesome.
Yeah, and so we actually had a good talent pool, you know, and they came to work in the early days at Akamai. But part of the theory that, you know, we developed was to make it be fully distributed and really fault tolerant on the basis that a lot of things could break, and we had the theory say, okay, it's still, the system will still stay up and work. And that is critical because there weren't single points of failure, because sure enough, a lot of things did break, and then but the system would still work.
It's really extraordinary because you were imagining a system of scales much bigger than what was possible at the time, with an application scope much bigger. And I think the reason everything came together so well is because you had a kind of an interdisciplinary approach, right? You had the theory, you had the system side, and then you had the World Wide Web Consortium who presented the important challenge. This is one of the secret ingredients that I think remains very important for how CSAIL advances computing. This multidisciplinary approach to computing with people who are passionate about different sub-areas of computing. How important was that for your group? How easy was it to set these collaborations up?
It was great. That's the way CSAIL was and it is. I think the collaborations are very powerful, and it made all the difference. You know, without that, we wouldn't exist, and a lot of advances wouldn't take place. But the interdisciplinary research, all the way from theory to real practice, makes a huge difference.
It's really extraordinary to think about this kind of end-to-end comprehensively. So another thing that MIT and CSAIL cares about is real-world impact, is taking our results, our theories and algorithms and ideas developed with a long time horizon and making them relevant. So how did you know that your algorithms would be so relevant? How did the story of Akamai start?
We were naive and, being theoreticians, just thought it should work in practice. In terms of becoming a company, that wasn't our goal, initially anyway, but we entered the 50K contest, mostly to learn about how do you write a business plan. And literally got books out of the library, business plans for dummies, And we learned a lot in the 50K. We met venture capitalists. None of us knew what a venture capitalist was even. It's hard to believe now, but that's the case. We met with industry experts and got a lot of advice. Now, at the end of the 50K, we actually had offers to start a company, but we decided not to.
Did you win the 50K?
No, we didn't. It's sort of urban legend is we did, but we didn't. We made the final 6, which we were pretty excited about. They only announced first, second, and third. We weren't announced. I'm pretty sure we were last among the finalists just because we had no business experience and really saw much better business plan presentations.
But you had the tech and you had the vision and you had the impetus to change the industry, right? I mean, it was extraordinary.
Yeah, we had good algorithms, no code. We thought
no code.
No code. No,
when did you start implementing?
Our idea was to get other people to use the technology. So during the 50K, we went and talked to the ISPs of the day, AOL, UUNet, HarvardNet here locally, and we wanted to get them to use our algorithms, which meant they would have to code it up and make it all work. And they talked to us because we came from MIT and it sounded interesting. But then after they heard what we were doing, they said, everybody knows distributed computing doesn't work in practice. It's an ivory tower concept. Thank you for coming, but please go back to your ivory tower. So we totally struck out. And then we actually decided not to form a company because we weren't sure that we could actually get the technology from theory and algorithms to work in practice. Danny, co-founder, he wanted to be a theory professor. It would have been a great one. I liked being a professor, here. It's really fun. But we kept on thinking about it and, then started talking to the big names in content delivery, the websites that had a lot of people coming to them. And they said, look, if you build this, we would buy it, because we need our websites to be faster. It makes a big difference to our business. And so then it got down to the point where the only way we were going to get the technology out in the real world is to do it ourselves. And that meant forming a company, writing code, and building, the infrastructure.
So how did you decide then to form the company?
Well, we decided that, this is a very rare chance for us to have a difference in practice. I mean, theoreticians, they do very cool stuff, but most of what we do isn't really useful in practice and takes a long time if it is. Now the cryptographers have done amazing things. You look at public key cryptography and the work there, but most of theory doesn't cross over, and this was a rare opportunity. And we did believe it would work. So we decided, okay, we're going to bite the bullet and step away from MIT, which is sort of our nest, and we hired the former students, the programming team members, and went to the incubator space next door and started the company, got funding, from angels at first and then the VCs. And then we were on our way. And sure enough, the theory did work once we got it coded into algorithms.
You had proofs, right?
We did, yeah. And then we took off pretty quickly at that point.
And so how did you build the company into the giant that it is today?
It was great during the dot-com boom because money sort of falling off trees for investment. It didn't matter that the company was profitable or not. But then you had the dot-com blow up. And that was very, very difficult because now you had to become profitable. We almost went broke. Worst of all, by far, of course, Danny is killed on 9/11. And that was just devastating for us. Our customers are going broke because most of them were, dot-com crazy companies. So we really it's the people we had in the company then that made the difference. The technology really did work, and it was a matter of getting real companies to buy our services. And we were fortunate that we were able to do that in a way that we started making money just in time. Then we grew.
So the cloud services came online around 2007. Was that important for your company?
Yeah, it's interesting. We were actually working on edge computing, distributed computing, way before AWS. We were doing that in 2001, 2002. But then, of course, the dot-com blow-up, we had to make massive cuts, so we put that off to the side. And AWS, it's amazing the business they've built. Now you have GCP and Azure as well. Those guys are among our largest customers today. We do a lot of delivery for them, and we do their security. And now we're actually getting back into core compute. So we have major data centers like AWS would have, and we're actually now in the process of deploying, VMs and containers into edge regions. So we have today over 4,000 edge locations in 750 cities. And the goal this year is to be able to have 100 of those cities where you can run your VMs and containers.
Does the machine learning revolution have an impact on you and on your customers, on how you do things?
We've been using ML and AI forever in our security solutions. Anomaly detection, is it a bot, is it a human? If it's a human with the right credentials, is it a thief that stole the credentials? All those kinds of things AI is pivotal for. Now you got some pretty cool advances with Gen AI and LLMs and a lot of use cases there. I would say today it's giving a quick leg up to the attackers because you can use that to generate code and you can train it about malware and you can train it how to get around the defenses. And so anybody now can make great or really dangerous malware. And that's not good. And so we're already seeing penetrations into the big enterprises rapidly increase.
What should we do about it? Because we have to stop the supervillain.
You need more than ever defense in depth. You need more than ever early detection so you can detect the malwares in. And we do now have the market-leading solution to do that. It's micro-segmentation. You've got to have an agent or a firewall on every single app you have, every single device. And it's got to govern what that app can talk to. It's got to filter the communications because the malware is in your internal network. And you really got to know where it is and you got to stop it from spreading. Ransomware is not so bad if it just gets into a server. It's when it spreads everywhere you got a problem. Same with data exfiltration malware. It gets into your HVAC system. That's often where it'll go to call home. Not bad yet. It's bad when it goes and grabs all your data and sends it out, to the command and control. So I think micro-segmentation and the notion of very localized internal firewalls is very important.
What do you see as the company outlook for the next 3 to 5 years?
We started in content delivery. It's not our biggest business now. Security is our biggest business. Yeah. And I think you go 3 to 5 years, maybe compute, cloud computing, because that's such an enormous market, becomes the leading business for us. But really is all those things put together in what is the world's most distributed cloud. The hyperscalers are much bigger, obviously, but they're centralized. They started in a data center and then another, and they have a small number today. And Akamai started fully distributed, and we're in 4,000 locations, and now we're adding the cloud computing aspect.
Tom, you somehow managed to be the superhero CEO, a beloved teacher at MIT, and also a researcher. How do you manage to do it all?
Well, I don't really do research really anymore. Every once in a while, it's fun to talk to somebody who is. And the teaching I do every other fall for the 1200 or 120, they're going to change the number. And I do that instead of serving on other corporate boards. Most CEOs, you serve on a couple other company boards, and it's about the same amount of time. But I think much more interesting and fun to teach, 1200. It's a chance also to talk to the computer science students about, mathematics in a way that I think is important for them and interesting, actually.
What are some of the pieces of advice you have for the students who aspire to be as impactful and successful as you have been?
I remember advice I got when I was, their age. was actually a Nobel Prize winner, talking to young kids interested in science. And he said that always you want to keep your eyes and ears open and your brain turned on. Because you never know when there's going to be an opportunity or a challenge presented that if you're listening to it and you see it and you're thinking, maybe you can make a contribution and solve it or help. And I thought that was pretty good advice. I think keeping an open mind, just because something seems impossible doesn't mean that it is. And you know this, like sometimes research problems become homework problems, right? Because once it's solved, if you tell the student they got to do it for homework, they figure it's solvable, and then they do it. And I think that's true in research or tackling, hard problems. I remember somebody, a knowledgeable guy in the field, once saying that the only reason Akamai was successful is because we were too naive to know what we were doing was impossible and that couldn't be done. And yeah, we were naive, and it just, well, this made sense to us, theoreticians, and you don't worry about being in the box as a theoretician. And yeah, it turns out it's possible.
You got to have guts.
You do have to have, tenacity, that's for sure. You got to stick with it. You want to listen to the naysayers and process what they say, but if you think it's what you're going to do still works, you got to keep at it.
What about education, the education side? What should the students focus on? What do you see as the role of theory versus systems versus other subfields of computer science?
I do think they're all important. Of course, I grew up in theory, always partial to that, and the rigor, I think, is really important. I gained a lot of appreciation for systems, through Akamai. There's a big difference, I learned, between, writing an algorithm on paper and proving a theorem and developing code that's going to work in the real world. Very, very different endeavors, and I gained a lot of respect for what the systems folks do and the engineers do.
Tom, thank you so much for all your contributions to us at MIT, to computing, to the world. You're really such an inspiration, and I'm going to try really hard to have more interdisciplinary collaborations within CSAIL to look for the next nugget that could be as successful as Akamai.
Awesome. Well, CSAIL is great. Really appreciate your leadership here because it is a gem here. Just really, really valuable, I think, for humanity broadly.
Well, it's the people who make it wonderful. And you are one of our superheroes. So thank you, Tom.
Thank you.